And share my screen. And we're gonna grade the quizzes in class just like normal. Probably go a little bit faster today because we got a lot of important material to cover. And my hope is that this quiz was a little bit easier than some of the previous ones, and the one that you'll have next week, the second object-oriented programming quiz, you can expect to be have a lot more trickiness going on inside of it. This one is, I think, if you knew what was going on, then it was pretty easy to predict what these programs are doing. So here again on, this is problem number 1. And for all these problems, like normal, I did my best to copy and paste them over, but I may have made mistakes. So make sure that double check me if things look weird, let me know. We're defining our class up here. And as soon as we have a variable that is defined inside of a class, that becomes an attribute of the class object over here on the right hand side. And then, so line 3, creating a new object here. This is a foo instance because it was created with the foo constructor. And then on line 4, setting the attribute message inside the foo instance that A references. And similarly for 5 and 6, doing that with B. And then line 8 down here, when we do a.message, we ignore the message in the foo class, we ignore the message in the B instance, and we only care about the message in the instance that A references. And so we get hello world as the answer for number 1. Any questions on problem number 1? Number 2, here we also, in our class up here, are defining a class level attribute, an attribute that applies for the whole class, but now we're also defining a constructor right here. We're scrolled over, there we go. So line 5 right here, we just executed line 1, and we're on line 5, creating the foo class object over here. Line 5 is going to create the A instance for us, and we go inside of the constructor up here. And we do self.message equals message right here. The message right here, the value of message is equal to none. And so when I press next, we get the message of none over here. This does, in fact, have a message attribute. The message attribute is just equal to none, which is different than having no message attribute at all. Coming back here now, the constructor's finished running. The A attribute is fully defined, or the A variable is fully defined. Similarly for B, we will go into the constructor up here, but now set the message equal to Hola Mundo. And then coming down here, when we actually print things, it's foo.message. So we don't care what's inside the A and the B instance. We only care what's inside the foo class. And the foo class does happen to have a message attribute of Salve Mundi. And so that's what the answer is for number 2, Salve Mundi. Any questions on number 2? Number 3. So we define our foo class. Now there is no message attribute inside of here being defined. No message attribute over here. Line 5 right here creates our A instance with foo of hello world. And we have this, oops, I scrolled, where are we at? I just executed or began executing line 5 right here. We're going inside of the constructor here. The message value inside the constructor is hello world because that's what's being passed into the constructor function right here. Come down, we have if message. Any string that is non-empty evaluates to a what we call a truthy value in Python. And so our string hello world is not empty, it is truthy. So we go inside the if block right here and say the foo.message equals message. Importantly, this is foo.message right here and not self.message. And so when I execute this line right here, you'll see that the foo instance down here does not have a message attribute added to it. Instead, the foo class object up here has the message attribute added to it. And so when I come down here, line 6, b equals foo, press next, go inside of the class here. We have if message, message now is equal to none because nothing was passed in here. None is a falsy value in Python. We do not go inside of an if statement if the condition is none. So we will not execute line 4. We will just end the function, come down here. And so the b instance also does not have a message attribute. But when we on line 8 try to find the message attribute for the b instance, we will see that there is no attribute here. And so we will go to the class up here and find the message attribute for the class and acquire that to get hello world as the answer for number 3. Any questions on number 3? A lot of subtle, tricky things here. Maybe not testing your ability to compute in your head so much as just your eye's ability to zoom in on the spots that have portions of the code which have significant semantic changes depending on what's going on. Number 4 over here, last problem. So here we're defining an empty class, has no attributes inside of it, and A and B, there we go. Everything has no attributes inside of it. And then on line 5 right here, foo.message equals hola mundo. And so the foo class object up here gets the message attribute of hola mundo. And we come to line 7 and a.message is what we're looking for. A has no message, but similar to last time, coming up to the foo class because this is a foo instance. And so when this does not have the attribute we're looking for, we look at the class object for the corresponding attribute. And here we see the message attribute. And so we print hola mundo. Any questions on anything about the quiz? Question, yes. Yeah, so the question is, if here we did not have an if message, but our constructor looked something like this, then what would happen? And I'm just gonna put a breakpoint here on line 8, so we will run both of these constructors right here. And here, when we do this foo.message equals message inside of this constructor right here, we do in fact get a none value being assigned to message. So this here would have overwritten what this up here did if we did not have this if statement right here. This is a reasonably common pattern for things inside of Python in constructors. By reasonably common, I mean like, I don't know, 1 out of 20 to 1 out of 100 classes will do something like this. It'd be extremely rare to have something like this without the if statement. But so yes, in this case, the answer would have been none if there were no if statement right here. Each problem's worth 1 point. So total it up, make sure your name's on it, and get those passed up to me. After the quiz, what we're going to be going over next is the homework assignment and how to navigate it in code and with Vim. And so if you want to try to be following along with that, bring up your containers assignment in the terminal on the Lambda server. Any other quizzes for me? Yeah. Okay, so in just a little bit, we're going to be moving over to a terminal session here, again, with the containers repository set up and looking at the BST branch for that your homework assignment is going to be in. We'll get to this in about 5 minutes or so. So if you want to be following along with what we'll be doing in class here, what I'll be doing in class, then pull that up to have on the Lambda server in your containers repository on the BST branch. Before we do that, some high-level things on our README file up here. Just a quick typo fix. I hadn't pushed my full edits last time, and I mentioned that we're going to be having 3 more assignments that are very closely related to each other, starting with this first assignment that we're going over right now, this homework that we'll be going over today, and that will be due the week after spring break, is going to be worth 32 points. The follow-on homework also worth 32 points. And then the third homework assignment, so 4 weeks from now due, it'll be worth 64 points. And again, there'll be no collaboration allowed on that assignment in any way whatsoever. I won't be answering any sort of detailed questions about the assignment. But again, all of these assignments are really building off of each other, and you'll be working in the same repository, working with the same classes and objects that you're creating. And so the purpose of these first 2 assignments is really to get you the comfort and ability to solve these sorts of problems so that on this assignment here, you'll be able to do it on your own. So as you're working for the next 2 assignments, don't just try to focus on completing the assignment, but also focus on making sure that you would have been able to complete the assignment without consulting any other resources. So another resource that you will not be allowed to use on this assignment here is, for example, QCL tutors. You will be 100% on your own for this third assignment down here. And so you'll want to, again, make sure that as you're working on these assignments, not just being focused narrowly on the assignment, but also a little bit bigger picture on making sure that you would be able to solve a similar assignment on your own. Again, I think this first assignment's relatively hard because it's going to be big and different and a lot of new stuff. This second assignment is definitely the hardest of them all. This third assignment, in terms of like absolute difficulty, sits between these 2, but most students will find this one to be a little bit easier than this first one, just because the first one is a lot of very, very new stuff. High-level idea, what we're talking about these coming few weeks are recursive data structures. Again, your object-oriented programming quiz number 2 has a lot of questions on recursive data structures. We will not have assignments on what are called linear data structures, but they are in the object-oriented programming quiz. And from a student's perspective, the reason they're interesting is because they come up a lot on technical interview questions, especially on the easier end of those technical interview questions. We're not going to have an assignment on those, though, because in the Python world, for various reasons, they're never actually used in practice. They're only used in the context of a data structures course or interview questions based on a data structures course. And so if you're preparing for an interview, it'd be good to review those a little bit. Here's some videos that I recommend to review that. But our assignments are going to be on what are called tree data structures, recursive data structures for trees. And this first assignment on trees will be on this generic binary trees and this thing called the binary search tree. And then these other 2 assignments will be building on sort of slight variations on these concepts here. There's going to be 6 big picture algorithms that you'll need to know for this first assignment. You can find them here. These are generic algorithms for every binary tree, 3 generic algorithms for every binary tree, and then 3 algorithms specifically for what are going to be binary search trees. Our binary trees are going to be a subclass of our binary search trees, and they will also be a subclass of the AVL trees and these heap trees. And so by implementing them with this subclass, superclass architecture, we're going to get all these algorithms in some sense for free when you start these next two assignments down here. I'm gonna switch over to the code here for a second so we can see, start getting a feel for what's going on with the code. Here I'm in the containers repository. There's still this containers folder and this tests folder. If we look in the tests folder, there's now two new test files right here, tests for binary tree, tests for BST. BST is a common acronym for binary search tree. So I go back and forth between saying binary search trees or just BSTs. They're the same thing. And also in the textbook, it goes back and forth between binary search trees and just BSTs. If we do ls containers, then we have these two files right here, the binary tree.py and the bst.py. I'm going to open up in this containers. So I'm staying in the containers repository right here, and I'm going to open up, first of all, this binary tree.py file. And we'll take a look at what's inside of this file over here. Let me move this out of the way a little bit. Just to keep my screen a little bit more organized, on the right-hand side over here, this is still in the same folder, this terminal session. I've made the prompt a little bit smaller so that it's not filling up my screen. But if I have to run terminal commands, I'll be running them in this right-hand window over here, leaving Vim open on the left-hand side over here. In this, again, I'm in the binary tree.py file right now. This will be the first file that you'll need to be implementing things on. Inside this file, there are two classes. I'm going to use /class to search for classes. Here you can see that this is searching for, or finds the word class anywhere inside of a file. In Vim, Vim search supports regular expressions. You can search for an arbitrary regular expression. You can't do that in most other text editors. The beginning of a line, regular expression is the up caret like this. Up caret class matches the actual class definition at the beginning of a line. And now I can search easily between my two classes like this. Between all the files that you're going to be working with, so there's going to be 4 files that you'll have to be navigating back and forth between. Between all 4 of those there's about 1,000 lines of code that I'm giving you, and you will have to be writing, I think my solution's like an additional 200 to 300 lines of code. So the ability to navigate your files is going to start becoming very important on this assignment. And eventually, I think the largest project we have in this class is you're going to be implementing some things about the game of Risk, the board game, some AI for that. And that project has like 20 or 30 files inside of it with tens of thousands of lines of code they'll have to be navigating. Getting used to using Vim to navigate effectively will be very, very useful for you. Again, because this particular assignment is getting very large, not only, well, all the debugging techniques that you'll have to use are things that will be like just in the terminal. It will be impossible to use Python Tutor and any other tools to do debugging with. You'll have to be doing things inside of Vim and inside the terminal, and it's just not possible to do things any other way. So again, as we're going through, I'm going to mention a bunch of these tricks like searching for parts of the code to effectively navigate to your files here. You're not expected to necessarily memorize any of those tricks, but I would encourage you to incorporate them as much as possible into your workflow. So this binary tree file has 2 classes inside of it, this class node and this class binary tree. The node class is somehow a helper class for the binary tree class. For helper functions in Python, it's common or customary to put a underscore in front of them. For classes, that's less customary to do. So here, this node class does not have an underscore in front of it. You just have to understand that it is really a helper class and that it's this binary tree class that is going to be the most important one. Common pattern for these sorts of helper classes is, actually, sorry, before I get to that common pattern, I want to introduce our last class that you'll be working with, and that's in our other file. Throughout this assignment, you'll be having to go back and forth between many different files. I strongly encourage you to use Vim's tab feature to be doing that and not closing out and reopening Vim sessions. You will get very bogged down if you are closing and reopening Vim, but if you have multiple tabs open, then things will go very smoothly for you. So :tab E is how you open a new tab, then containers/bst.py. This is the other source code file that we'll be looking at. And again, GT is how you switch between tabs in normal mode. And here, this BST class is our third class that you'll have to be implementing. Here we can tell that BST is a subclass of the binary tree class because it's using this notation right here. And anytime you have a subclass and superclass relationship of things, we know that this BST class can access attributes or access methods inside of the binary tree class. That BST has access to everything inside of binary tree. Conversely, binary tree does not have access to anything inside of BST. So because of that relationship, it's good to start thinking about implementing the binary tree functions before implementing the BST functions. The BST functions can depend on the binary tree functions, but not the other way around. So start with these binary tree functions and then go to these BST functions. Gonna jump back over to Firefox for a second, and I'm gonna take us to the textbook. There's a reference section here at the bottom. If you click on this, and it's chapter 7, has all of the details about the tree data structures. And in chapter 7, this first 7.1 to 7.7, this is like the generic binary tree stuff. Up here, this is the generic information about trees, about the superclass. And then down here, starting at 7.11, the binary search trees up to 7.14. These are the things that'll be specific to binary search trees. The textbook actually has a fully working implementation of binary search trees and binary trees. You're welcome to borrow as much code as you would like to from the textbook. 100% okay to copy and paste things from the textbook. The difference between, there are some slight differences between our code, how our code is going to be working and how their code is going to be working. So I don't think you can actually just copy and paste things and have it suddenly work, but you can use their code as a very close outline for having the stuff in our classes work. Okay. Next, in order to talk about exactly what's going on in these classes, I'm going to draw some pictures, and we'll see how those pictures relate to the information inside of Python over here. And then I'll see where you can find similar pictures inside of the textbook. So I have just a window open up here that I can draw on, and a binary tree. So this is not the search tree, not the BST, but the superclass, the binary tree, is anything where it's typically drawn where circles are what are called nodes, and then we have left and right edges coming off of these nodes to other circles. And so this is an example here of a binary tree. Inside of each one of these nodes, we have values. Traditionally, we put integers here just to draw things, but your code has to be fully generic where it can support not just integers, but strings or any other type in Python. And in a binary tree, there's no relationship between any of these values at all. You can just have whatever you want in any location. Here, again, each one of these circles is referred to as a node. Each one of these lines is called an edge. And then with this particular node, if we're thinking about node 6 right here, this would be the parent of node 6. 6 has 2 children, child, child, and we would call this node over here a sibling of node 6 because it shares the same parent. And so as we're going through today, and as you're looking in the textbook at things, they will be using these terms. And I don't know, once you see what it is, it's hopefully mostly intuitive that like a family tree sort of relationship, you can predict what a grandparent might be or a grandchild, that if we added another node right here with maybe a -2 in it, then we'd call that a grandchild of that same node. So again, each one of these circles is an individual node. And so coming back to our binarytree.py file over here, this node class right here represents an individual circle. This self.value attribute, the value attribute represents the whatever we're putting inside the circle. So all of those numbers are the values. And then the left and the right over here represent edges between those nodes. So the left and the right, draw that in green. The left and the right are these edges that point to some other node object. If we have this node right here is an example of what's called a leaf. A leaf is a node without children. A leaf is a node without children, and the left and the right values for this, the left equals the none, and the right equals none. Here, this example node right here, this -5, this is an example of a node that is not a leaf because it has a child, but here the left value would be equal to none. It's perfectly okay in a binary tree to have a node that has a left child or a right child or both children or no children at all. Any combination is totally valid. The algorithms, the two important algorithms that we do on binary trees are what we call the height of the tree. So in this case, the height of this tree is 4. Sorry, one last definition up here I never defined. This is a special node, a node with no parents, a node with no parents is called the root. And so the distance from the root to its farthest away descendant, all the things below descendants, all of the things above ancestors, the distance from the node to its farthest away descendant is called the height of the tree. So distance from the root to farthest descendant. The height of the tree. And so that's the first important algorithm that you're going to have to implement here for the binary tree. And the next algorithm, the size of the tree, we'll keep it in red here. The size, or sometimes called the length of the tree, is the 1 plus the total number of descendants of the root. Which is maybe a fancy way of just saying that it's the total number of nodes in the tree. Again, for these definition sort of things, there's never going to be a quiz on the definitions. I'm never going to tell you to define what is a sibling or what is the difference between a leaf and a root node. But you'll see me throwing around all these terms, and the textbook will use all those terms, and your code has variables whose names follow these conventions. And so just having a good intuitive sense of all of these definitions will help you navigate the code better. Any questions on definitions or anything about the binary search tree? Oh. Great question. The question is that here, for example, we have like this child of -5. And the question is this a node or is this not a node? And the answer is that's a matter of convention. Convention determines whether you call this a node or not a node. For the purposes of your assignment here, it will not have a node instance that corresponds to a none value. If left, the way to signify that a particular node has no left child is just to set left self.left equal to none, and that makes it says that it doesn't have a child. Where'd it go? There it is. So this is all the high-level information. Oh, question, yes. Yeah, question is, can there be a maximum of only 2 children? And the answer is, because this is a binary tree and binary means 2, for this particular type of tree, every node can have at most 2 children. In general, you can have nodes or you can have trees that have more than 2 children. But it turns out that you don't actually get any benefits from that. The reason we're talking about binary trees right now, our motivation for this is, we'll go over this section of the README file right now. The motivation for binary trees is that it's related to binary search and sorting. But if you recall, binary search lets us check O-login time to find an element. And that's really fast, much faster than the sequential search, which was linear time. The downside of binary search was that you had to sort things. And then if you want to add new things into your container, you would have to resort it, and that would take a long time. What we're building up to is binary search trees. So we've talked about binary trees, but not binary search trees. But what binary search trees is let us do both insertion and deletion and finding all the possible operations that we want to do in logarithmic time. So it's like combining the best things about binary search without having to do all the explicit sorting. And one of the things that you saw in one of the runtime labs was that if you tried out trinary search, you got the same basic runtime as binary search. And so it turns out that if you try a 3-way search tree with 3 splits, you'll get the same runtime as a binary search tree. So there's really no advantage of going up to anything beyond 2. Okay. So in terms of how this relates to code, again, each one of these circles here is one of the node classes. And then if we come down here to the binary tree class, there is a root attribute of the binary tree class, and this is the only attribute of the binary tree class. So the binary tree class itself contains all of the nodes inside of it because it has an attribute just of the first individual node. And then all of the children nodes are going to be children of that node up here. Yeah, so we're going to talk about the binary search tree next and how that relates to the binary tree and the node classes. Again, because the binary search tree is a subclass of binary tree, that means that every binary search tree is a binary tree. And so every binary search tree will also have a root attribute that points to those particular nodes. The difference between a binary search tree and a binary tree is that every binary search tree must obey something we call an invariant. Every BST must obey the binary search invariant. And so what is the binary search invariant? It says that all descendants on the left of a node must have values that are less than the value of the node. And conversely or similarly, all descendants on the right of a node have values that are greater than the value of the node. So the key thing here is that on the left, everything is less than, and on the right, everything is greater than. And this is what's going to allow us to do our searches in logarithmic time. I'm going to draw out an example of a binary search tree. Again, it will also be an example of a binary tree, and we will see how this invariant holds and why it allows us to do fast runtimes. So here, if we have the number 5, then if we're trying to say also have the number 6 in our tree, the number 6 cannot be to the left, it must be to the right. If we have the number 3, that one would go to the left and not to the right. And then similarly, we could have, say, the number 4 right here and the number 2 right here, and say the number 10 and 11, 9, something like that. This is still an example of a binary tree because we have these nodes and they have left and right children. All of our same terminology as before applies. So we can still do things like talk about the height of this tree or talk about the size of this tree. All those things still make sense. But now, because we have this, this new property of the binary search tree invariant, we can do searches in a very fast time. If, for example, I want to find is the number 4 in my binary search tree, starting at the root right here, I know that, well, if I'm currently looking at 5, if I'm currently looking at the root 5 right here, I know that I don't have to look at all to anything to the right over here because all of these values over here are greater than the 4. So I can just not have to search all those things and come down over here to the left and only search the subtree to the left. I only have to search basically half of the tree. When I get to this over here, finding 4 on this subtree, then 4 is greater than 3, so I would go to the right and find that 4 is in fact in the tree right here. So it's only 2 steps that I have to do to find whether 4 is in the tree or not. And I don't have to consider lots of extra nodes. As another example, if we're doing say find of 7, then starting up here at 5, I would go to the right. Here at 6, I would still go again to the right. Then at 10 over here, I would go to the left. And then at 9 here, I would try to go to the left, but there is no child over here. And so we can say for sure that 7 is not in the binary tree, because if it was, it would have to be to the left of this 9. And there's nothing to the left of the 9, so 7 is not contained in the tree. This idea of going down only one branch of our tree, the idea of going down only one branch of our tree and making our algorithm faster that way is sometimes called pruning the tree. You'll see that verb thrown around. Pruning algorithms, or traversals. And the idea is by only going left or right, we can remove a lot of things from our tree, and we don't have to find them that way, or we don't have to search through everything in our tree. Going over, so this find algorithm here, this is something that you will have to implement for your binary search tree. We're going over it at a high level at this point, just looking at the pictures. You want to make sure that you can fully understand the pictures that go along with any of these algorithms before starting to try to understand the code that corresponds to these algorithms. So at this point, any questions about this picture? Yes. Yeah, it's a great question. The question is, when we did the find 7 over here, and we said that we got to this location right here, and there was no child to the left of 9. So why is it the case that we can say for sure that there is no 7 in this tree? Because maybe it turns out that maybe there would be a 7 here. Because it would be fine for 7 to be a left child of 11. And then, but how do we know that 7 can't actually exist in this tree? And the answer is because 7 is to the left of 11, but it's still to the right of 10. That in order to get to the 7 down here, we would first have to go to the right of 10, then to the left of 11. And the binary search tree property is not only about the children being less than or greater than, it's about all possible descendants on the right-hand side or the left-hand side being less than or greater than. So because we have some descendants over here, or if we were to have a descendant of 7 over here, then this would not be a valid binary search tree because it would break the binary search tree invariant. Good question. This idea of invariance for your data structures is a crucial thing to make sure that you're understanding every time you see a new data structure. Fully understand these invariants and these sorts of edge cases like this about the invariants, because it can really trip you up if you don't have a full grasp of the edge cases like this. I'm going to switch over to the code for just a second. And we're going to look at the binary search tree class here. And I'm going to do a slash right now, search for the word invariant. Here we go. Satisfied is what I used in the code. Is BST satisfied? And this function right here is what checks to see, is the binary search tree invariant holding? Is it actually satisfied on your particular tree or not satisfied? And anytime you're implementing a data structure that has an invariant associated with it, some sort of check to see is that invariant holding is always the very first thing that you'll want to implement. So after getting the binary tree parts working, the next thing to do, or the very first thing to do about the binary search tree, is making sure the BST satisfied invariant is actually working. Because if you're trying to work on your, say, insert code or your find code, and you have a tree that is somehow messed up, like that puts a 7 over here when it shouldn't, then there's no way that your find code will be able to work because your tree doesn't satisfy the invariant. So always the first thing to work on is your as a helper function, a debugging function that checks to see whether an invariant is satisfied or not. And you really, really want to test this well, make sure that it works well. In terms of test cases for this code, I'm going to, again, open up more test cases. So this :tab E over here. And then now it's tests and test underscore binary tree and :tab E tests test underscore BST like this. And we're going to see how the test cases work for these particular files. Just to give you a sense about how complicated these test cases are, so I pressed Shift G here to go to the end of the file, 152 lines in the binary tree test cases, Shift G to go to the end of the binary search tree test cases, 323 lines. You can see there's a lot of, these are still using the hypothesis tests, the hypothesis library for generating tests. And so there's not going to be necessarily specific test cases that you have to pass, but there are going to be these randomized test cases that cover all sorts of possibilities. That's true for everything except the isBST satisfied function. Here at the very top of this test BST, there's a bunch of test cases for isBST satisfied. And once these test cases pass, then that function is actually used to check that all of your other functions are correct, that like whether you can delete from your tree and insert from your tree correctly, it always calls the isBST satisfied after doing an insertion or deletion in your tree to check whether it's correct. So there's no way of passing the test cases, the other test cases, until you have this function fully working. When thinking about debugging these functions, it's always good to have a concrete example of a class in mind, or an instance of that class in mind, and work on that concrete example. Do your debugging specifically on these concrete examples, and then go on to the hypothesis tests once you're confident that it works on these concrete examples. So I'm going to show how that works here for specifically for the binary tree class. I'm going to show how some good debugging techniques for this binary tree class. And in order to do that, on the right-hand side over here, one thing that I'm going to do anytime you're working with the sort of example code, it's good to load it up into interactive Python to work with it. So containers/binarytree.py like this. So I'm just opening up my binary tree file in interactive Python, and then I can create nodes and work with the nodes. In this case, in my binary tree, there are no example nodes for me to work with. And so I could do something like in equals node. Well, here our constructor requires a value inside of it. and then try to manually build up a node like this in dot left equals node of 12 in dot right equals node of 13, and manually build up nodes. Anytime you want to display your nodes here, if you just type in by itself in the repr in the in interactive Python, recall that it calls the in._repr function in order to display that. In this case, that function's not implemented, and instead the node class implements a str function, magic method str. This is whenever you use the string function, convert the type into a string. This is how it calls this string function right here. And this will be a very useful tool for you for visualizing how your code is working. So we're going to go over visualizing these node objects next, so that you can translate from these string representations back and forth to these picture representations in order to check things like, is your binary search tree property valid, or is your code doing what you think it should be doing? Does your tree look like what you think it should look like? In this case, what this representation looks like is every set of parentheses is a node object, and the dashes separate the children from the parents. So the easiest way to visualize this is to find the nodes that don't have any children, so like this node here and this node here, and then start by drawing those two nodes. So do an example of that. So here in our code, we had a 12 and a 13. A 12 node and a 13 node. These are both leaf nodes because they have no children. I know they have no children because they're the dashes over here have nothing between them. There's no child here, no child here. Then in order to figure out what these leaf nodes connect to, I want to find the parent of those nodes, and this 10 over here is the parent. This is the left child of the 10, and this is the right child of the 10. So coming back over here, drawing the 10 like this, and we get the 10 and the 12 and the 13. And if we were looking at the code up here that I used to create this tree, in equals node 10, in dot left is 12, in dot right 13. This up here matches what we created over here. The 12 left child, 13 right child, 10 the parent. So again, if you have a node, visualizing it with the string function is the very important debugging tool in order to know what to expect from, say, your height and your length functions. In this case, though, so it's not the worst thing in the world to make your nodes manually like this, but it is, like, once you start getting into interesting trees, it can take a long time to generate your nodes this way. Inside of the binary tree test, there are a handful of these nodes automatically, or that I have already created for you, that are longer and interesting in various ways, and I recommend using these as your initial tests. The easiest way to test these nodes is to copy and paste from Vim over here on the left to the terminal on the right. In order to do that copying and pasting, though, if I try to copy and paste just like this, you'll see that I'm getting those numbers. So again, the :set no number like this will remove those numbers. And now I can copy and paste this over here, and I'll have that underscore example1 node to access. Again, if I just type it like that, it will not give me a useful representation, but if I convert it to a string, then I'll have a I don't know, it takes a second maybe to parse through this and think about what it is, but now you can actually go through and try to draw the tree that corresponds to that and figure out what it actually looks like. Question, yes. Yeah, question is, how do you determine which one is the right node and which one is the left node looking at the output of the string? And the answer is the thing to the left is the left node and the child to the right is the right node. So here 10 is the parent, then you have a dash to separate the children. The next thing is the left child. Starting at the opening parenthesis, finding the corresponding closing parenthesis, that is our left child, and then a dash, and then the next thing is the right child. Yeah, you're correct though to point out that these are not binary search trees. These are only binary trees, and so it does not satisfy the binary search tree invariant right here. That this 12 is greater than 10, so it should not be to the left of a binary search tree, but it is okay for it to be to the left in a ordinary binary tree. Maybe so here, this example one. This is a binary tree and not a root. See that it was created with a binary tree up here. So 1 GT switches me to the first tab up here. I was over here in binary tree. In order to, rather than having to scroll through all of these things, if I type the number, then GT, it'll take me directly to that tab number. So 1 GT, 3 GT, 1 GT. And in order to find, again, my class, up arrow, class, ZZ, center, I'm going to try to find the function that corresponds to the str function. So /_str. There we go. And here is what the string representation of the binary search tree does. It just gives me the string of the root node. So the example one here, string of that, same as example one dot root. You get the same exact representation printed out. For all of these different functions that we're talking about, so talk about with the height, for example, there are always going to be some sort of pseudocode or hint about how to implement these functions. And every function that you have to implement has a fix me inside of it that just says implement this function. There are many functions that I provide for you. So these things called the in order and pre-order printing functions, I am providing those functions for you. And so you don't have to implement it. You only have to implement the functions that have a corresponding fix me inside of it, which there are a lot of them, but not everything. For the node class in particular, there is nothing that you have to implement inside of the node class. It's only functions inside of the binary tree or inside of the BST class. So let's come back to our height function. And actually, before we, the hint for the height is look at the length. So let's take a look at the length function first. We have pseudocode right here for our, this length helper right here. We have pseudocode that I've provided for you. And then there's a very common pattern that this length function uses that I want to discuss. This length function, basically all the functions that you'll have to implement are going to rely on a helper function, where the helper function is a static method, and the helper function itself takes a node as input. The length function up here, the length function does not take a node as input. It's just the binary tree itself. So you can access it just by doing length of, in this case, example one like this. You have this nice interface to it. We're getting an error because it's calling the length helper right here, which is not implemented. But the length function itself calling this length helper function. The helper function takes a node as input. All of these helper functions, all of these static method helper functions will take a node instance as input instead of the binary search tree as input. And so the convenient, easy to use function is just going to call the helper function on the root node itself. In order to use this helper function, so I'll try calling this helper function manually. If I do binary tree like this, and then pass in, this is my in value right here. In value is my node object, so binary tree of in, whoops, that's binary tree dot length helper of in. Binary tree has no underscore length helper, no attribute length helper. Binary tree has no attribute length helper. Length helper. Binary tree. GG. Next, here it is. So binary tree. Well, so the error message I'm getting right here, this attribute error, you shouldn't be getting this when you call the functions. So let's dig in what's going on right here. The attribute error is, again, anytime you have an object to the left of a dot and the thing to the right of the dot is not an attribute of that object. One of our debugging tools in the terminal is this dir function, which will tell me all of the attributes of a class. So here are the attributes of this binary tree class. And so here's binary tree dot binary tree length helper of in. There's our way to call it right here. Back to the length helper. And I'm just going to start off by adding a return 1 over here, save that, and make sure that whatever changes I'm making to the file are in fact coming over here to the right-hand side. And so if we rerun this immediately, you'll see that there's no changes taking effect. Anytime you want to save your file over here and rerun it over here, you have to close out of the interactive Python and rerun it like this. And now if I press the up arrow, go back to here, you'll see that I get this name error about in not being defined. That's because I defined in manually over here on the right-hand side. I defined in manually up here. And so if I want to have access to it again, I have to retype it all. And so it'll be easier just to get my example 1 and use that. And now run my binary tree helper on example 1. There we go. Underscore example 1, and we get the 1 down here that it is that it's outputting. The way that the length function should work, the idea of it is, so the pseudocode here is that if the thing that we pass in is like a valid node, so if node, so basically if it's not none, then we'll want to return 1 plus the length helper of node.left plus the length helper of node.right. So the size of our node, the number of elements in our tree is 1 for the current node plus however many nodes there are in the left side plus however many nodes there are on the right side. And eventually, following this recursion, we need a base case. Our base case is going to be whenever we get to a leaf node, and in that case, we will just return none. Or return 0. If node, else return 0. That's my attempt at a base case for those leaf functions. Again, I'll rerun this. It's not going to do anything over here on the right-hand side because I have to Control D, up arrow, reload this thing, come back over, get my test case function that I want to run on, paste that in, up arrow, up arrow, up arrow, up arrow, up arrow to my function call right here, and hit enter. And we're getting this name error now. Binary tree length helper not defined. So this, what do we use here instead of length helper? Let's do our binary tree dot length helper. Even when I'm inside of the class, I'll have to do this binary tree dot in order to get access to that helper function right here. So let's try that. Control D, up arrow, rerun, recreate my node. Recreate all this, hit enter, up arrow, back here, hit enter. And now we're getting this attribute error. So we're, I don't know, making progress. The binary tree object has no attribute left. And here, when I'm running my binary tree dot the length helper right here, I'm assuming that it has the node dot left over here. Maybe that node dot left doesn't exist yet, and so we'll need to check something like return equals 1, and then if node dot left, or rather, I'll try binary tree node dot left. So if that thing exists, then we'll do ret plus equals whatever we get there. Except attribute error pass. So we do nothing if we were getting this attribute error. We're getting the attribute error because the node dot left didn't exist. So we're only going to recurse over here if the node dot left does exist, add it to the ret over here, and then do the same thing for our try. Ret plus equals all this again, and then accept attribute error pass like that. And now we'll see if that takes care of this attribute error over here. Control D, up arrow, rerun this, come back over here, rerun my code. I misspelled attributes. 1GT. Yes, so 166G. Escape, 166G, take me to line 166. And find find TT attribute error, colon W, save, rate, switch over here, Control D, up arrow, rerun. Let's get our example going. Paste that in. Up arrow, up arrow, up arrow, up arrow, up arrow, up arrow, up arrow. There we go. Hit enter. Unsupported operand types plus equals for int and none type. One of the difficult things about these recursive functions and implementing them is figuring out where exactly the error messages are happening on here that we have. Again, this is called the traceback over here on the right-hand side of the stack of all of the functions that we've called. So this is the equivalent thing that we were visualizing previously in Python Tutor. Now we don't have the visualization of it anymore because there's too much code to fit inside of Python Tutor, so we can't even get the visualization. And we're going to have to interpret this this call stack information over here to get that back. And I think we are basically out of time, probably a little bit over. So I'm going to make a video similar to how I did for the sorting assignment, going over some more of those debugging techniques and implementing some of these functions for you. Yes. If anybody has questions about anything, then happy to stay after and get those answered. But otherwise, that's it for today.